Namaste everyone. Welcome to second PUC physics class. We have studied in the previous class about what are the differences between conductors, semiconductors and insulators, correct? And regarding their resistance, conductivity. Namaste, welcome to the class. So we are in the last chapter of the second part. So we have studied about the introduction part of the semiconductors. Why semiconductors are important, we will come to know about that later. So we have seen about the resistivity of conductors, semiconductors, insulators, why are they differentiated, what is the actual structural difference, that energy gap, conduction band, valence band, and what is the energy gap in insulators, greater than 3 electron volts. So electrons can't go to the conduction band at all, so insulators remain as insulators forever, and semiconductors have very less energy gap. So if needed, electrons can be made to go to the conduction band. So it acts like a conductor at room temperature, but it acts like a very not a very good conductor, but somewhat like a conductor at room temperature, but it's a perfect insulator at 0 Kelvin. But insulators remain as insulators forever. That energy gap is 0, and conduction band and valence band overlap in the case of conductors. So a small energy in the room temperature is enough, and it can have plenty of free electrons. It's always remaining as a very good conductor. So that is the situation. So we differentiated it, and we know what are the values of conductivity between for resistivity for conductors, semiconductors and insulators. So that difference is very important. That is in the notes what I have given, right? Now, now today we will see what are electrons and holes, and we have seen in a metal, in a conductor, all metals are good conductors. Electrons, free electrons are the charge carriers, whereas in a discharge tube, electrons and ions, positive ions, and in electrolytic solution, both positive and negative ions. In semiconductors, charge carriers, that means which are responsible for the flow of current, electrons and holes. What is a hole? Absence of an electron is called hole. Now remember, holes are always found in valence band, lower energy level. Energy level of holes are less. Electrons are always found in the conduction band. I am talking about free electrons, charge carrier free electron. Because if an electron wants to be free, if it is in the valence band, it is not free. If it wants to be free, it has to go to the conduction band. When it goes to the conduction band, it will be free, and it is a charge carrier. A vacancy is created in the valence band. So holes are found in the valence band. Now, these holes are not permanent holes. Electrons can come and occupy that hole. Now what do you mean by actually hole? Suppose you take silicon or germanium. They are all tetravalent. What do you mean by tetravalent? In the valence band, there are 4 valence electrons. There are 4 valence electrons in the valence band for silicon and germanium. Now, these 4 valence electrons, what do? If you ask valence electrons, why can't you be free? Why can't you move inside the material? They say, sir, we are engaged in bond. What type of bond? We are getting exchanged between the 2 neighboring atoms. So we are involved in forming the strong bond between the 2 neighboring atoms. How it is so? All are tetravalent. See, tetravalent means a silicon or germanium may not contain only 4 electrons. There are plenty of electrons. Out of them, the outermost 4 electrons are engaged in forming the bond. Now, suppose you take a silicon. Silicon is a semiconductor. It is tetravalent. There are 4 silicon atoms in the neighborhood. So here and here. And there is, for this silicon atom, there are 4 silicon atoms in the neighborhood, like this. For this silicon atom also. So if you go on drawing it like this, it is never ending, right? So every silicon atom has got 4 neighboring silicon atoms. So this silicon atom says with this one, can we have a friendship? So let us call this as A, and this is called this as B. A asks B, can we have a friendship? Yes. B says yes, we can have a friendship, but one condition. You have to give me one electron and this has to give me one electron. A asks one electron with B, B also asks one electron with A. So there is an electron exchange. That electron exchange makes the bond stronger. As if we give something to our neighbor when they are in difficult situation. Similarly, when we are in a tough situation, they give something to us. Either we help with each other. That makes the bond stronger. And when they are in a tougher situation, if you are simply sitting quiet and looking at them and making fun of them, the bond doesn't become stronger. So neighbors are always should be stronger, right? The strength of our life depends on the neighbors also. If the neighbors are stronger, we are also stronger. Similarly here, silicon neighboring atoms will start exchanging electrons, and this silicon thinks of, I want to give an electron. Which electron I can give it to the neighboring atom? It is only the valence electron, the outermost electron, because they are ready to do the work, and outermost electrons are exchanged. And in the diagram we show it like this. This electron has given one, this silicon atom has given one electron to this silicon atom has given one electron to this. So that is shown with the dots here, right? And remember, silicon has 4 valence electrons. This silicon thinks of, there are 4 neighbors here. One neighbor, second neighbor, third neighbor, fourth neighbor. I have 4 valence electrons. So why can't I share 4 electrons with the 4 neighboring atoms and make a bond so that all the valence electrons are now engaged? Okay. That is a very beautiful situation here. So one electron from this silicon also has got its own 4 valence electrons. Now the 4 valence electrons of these atoms are shared with the neighboring 4 atoms. That is why valence electrons can't behave like charge carriers. They are busy now. They are engaged in bond. They can't move from atom to atom. They can be only the bond forming electrons, exchanged electrons between the neighboring atoms. Similarly, this silicon. So this silicon has given one electron to this, right? So it can form bond with its own neighboring atoms. It can donate one electron to the neighboring atom and it can form the bond. Similarly this one. So if you complete this rangoli, it will be like this, but it is never ending. So we will have this completely now, right? Like this, here. So this bond is shown in the form of lines, that's all, right? Okay. Like this. So this silicon will donate its 4. One is already donated, one here and one here, one here. Similarly, this silicon will donate its own 4 valence electrons to the neighboring atoms, and the bond is becoming stronger and stronger. That's why silicon solid is solid. It is in the solid form. It is very strong. Anything remaining? Many things are remaining here. So here. Okay, this is so I can show it. It takes a lot of time. Okay, like this, here, and what about this one? Yeah, here one more, and here this one. See, everything is exchanged. If it only remaining, then you can draw it yourself, right? Okay, 4 here, 4. Everything 4, and here, yeah, here one more, correct, yes, like this. So 4 valence electrons are exchanged and the bond is completed. Yeah, you give me one pen, okay. You give me one pen, I will give you a chocolate. So that is what is happening between the students, right? Every time you give something and you take something from your friend, you give the notes, she gives the ice candy or ice cream or something. So something exchanged makes the bond stronger. So this is the actual silicon. This is the story again at OK, 0 Kelvin. Now tell me how many electrons are free. Only valence electrons you have. All the 4 valence electrons are busy in forming the 4 covalent bond with the neighboring atoms. And no electron is free. Who are there to carry the charge or carry the electricity to move from one end to the other end when a potential difference is applied. So if you take such a material and apply a battery, no current flows through it. Why? Because there are no free charge carriers. This is the story at 0 Kelvin. Now what happens if you bring this material to the room temperature? At room temperature, electrons can absorb heat energy. And usually atoms will absorb heat energy and they start vibrating. And you have studied in kinetic theory of gases also. And even for solids it is applicable. In gases, atoms will absorb energy and start moving here and there. Their kinetic energy will go on increasing. You know, kinetic energy is directly proportional to the temperature of the gas. And even in solids, but in solids, atoms are closely packed and there is no enough space, they can't move from one place to another. They start vibrating. As the heat energy is absorbed, atoms will start vibrating in a solid, and as they vibrate, the bond becomes weaker and weaker. If you supply extra heat energy, the vibration keeps on increasing. The amplitude of vibration increases, and at one moment, some bonds may break up. So when bonds break, these electrons become free, and they are called free electrons. How do you explain it in band theory? Very simple. So this is bond theory, right? And where is band theory? There is a conduction band and valence band. So valence band is filled even at 0 Kelvin and also at higher temperature, whereas the conduction band is empty and a very small energy gap, less than 3 electron volt, right? This is what is seen in semiconductors. Now, these are all electrons, but when you supply heat energy, electrons can absorb the heat energy and go to the conduction band. They go to the conduction band and this may be filled at room temperature. But when they go, they leave a vacancy called hole. That's what we define. So at room temperature, a semiconductor is partly a conductor, but at 0 Kelvin it's an insulator. Now what happens at room temperature here? The atoms will start vibrating by absorbing heat energy because they can't move from one place to another as if it is happening in gases. Here they simply vibrate, but as they absorb more and more heat energy, the vibration amplitude keeps on increasing. At one moment the bonds break. When the bonds break, electrons become free. So this electron comes out and it is a free electron. Now, but at the same time, this bond is not completed and it is requiring one electron to complete this bond, and we call this as a hole. A hole is created, just a name hole, that's all. You don't have a hole there. Hole is the absence of electron or requirement of an electron. Suppose there is some electron filling this vacancy, the bond is completed. But every atom wants to complete its bond. It doesn't want some vacancy to remain there. So this will happen only at higher temperatures, that means room temperatures, not at 0 Kelvin. So at room temperature, atoms will vibrate, lose their bond, and some free electrons are created. Now, I will study, or I will say one more bond is broken here and one more vacancy is created, and this is called hole, and free electron will move, right? This electron has nothing job now, it can move from atom to atom, it is not taking part in any bond. Now, the thing is, what about this hole? Holes also move. That is why we call there is current in semiconductor, there is current also because of movement of holes. So charge carriers in not insulators, semiconductors. Charge carriers in semiconductors are not only electrons but also holes, because holes move. How is it possible? Very simple. So this electron has gone. There is a hole created. Now some other electron looks into this hole. It says, oh, this bond is vacant and this bond is not filled. There is a requirement of electron. What this electron will do? That electron comes out of this bond and fills this bond. So when this electron moves from here to here and fills this bond, right, a hole is created here. But this poor electron, when it is coming from here to here in order to fill this bond, it doesn't know that I am creating a hole here. In order to complete this hole and complete this bond, this electron has moved. But that poor electron is creating its own hole. Now what do we say is, this is not called movement of electron. Why? Because this electron is a bound electron. By the time it came here, it was again a bound electron. It is not a free electron now. but this hole has moved, that vacancy has been shifted, so hole has moved, so this hole will start moving. And again this bond may be filled with another electron by coming over here, so this may be filled and the hole may be shifted here. So in this way, hole will not be found, that is absence of electron, absence of the breakage of one bond may not be found in the same atom. It may move from atom to atom, because electrons will start occupying that whole place, so that they will shift the whole place to the other side. Suppose in a 45 seat capacity bus, if there are only 44 people, what happens? Definitely one seat will be vacant. Say the first seat itself is vacant, just behind the bus driver. Then a person sitting somewhere in the back side, he feels that that seat may be better than what I am sitting now. Usually it happens so, right? Whatever we see finds to be very better than what we are having now itself, right? So that may be better. So what he will do, he will just shift his place from here to the vacant place. Now, if the conductor counts the number of people just before he is replacing, there are 44 people and there was a vacancy there. And once the person gets shifted there, again if the conductor wakes up and starts counting the number of people, again 44, but the vacancy has been shifted here. That's all. So if another person after some time feels that my seat is not better, it is raining heavily from outside and the water is getting in, and I will shift the place here, the vacancy has been shifted to the other place. So if one by one person starts filling that vacant seat gets shifted, because once that person was sitting in that place, in his own place, he is filled, right? Once he shifts himself and fills the vacant place, he is filling the place, but the vacancy has been shifted. So the shifting of holes from one place to another occurs because of the motion of the bound electrons. Not free electrons. It is bound electrons. Bound electron from one bond shifts to another place and fills the bond, thereby replacing the hole to the other side. So holes also, and we can't call it as a flow of electrons, because electrons are bound even before they shift and fill the gap or fill the broken bond, or even before that and even after that, they are bound electrons. Even before this electron comes here and fills it, and after filling it, it is a bound electron. It is not the motion of free electrons, it is the motion of bound electrons, but it is the motion of a hole. And when an electron moves in a particular direction, you know that hole moves in the opposite direction, right? When a filled person shifts from back side of the bus to the front seat of the bus, to the vacant seat, vacancy has been shifted to the back side of the bus. Back seat of the bus. So when the electrons move in a particular direction, bound electrons, holes move in the opposite direction. So in a semiconductor, holes are also responsible for the flow of charges. Holes carry current, but they carry current in the direction opposite to the flow of electrons. So in a semiconductor, both holes and electrons are responsible for the flow of charges, and hole is the absence of an electron, and they can move by using electrons when they fill the bond one by one. Okay, so that is the story in semiconductors. So they also carry current. And so in a semiconductor, suppose you apply a potential difference, a battery across a semiconductor, what happens is battery makes the electrons to move from one place to another. How do these holes move? Holes also move in the semiconductor, but they move in the opposite direction. But current is in only one direction. Why? Because we know that current is opposite to the flow of electrons. We always take positive charges as reference. So if you take a conductor, for example, forget about semiconductors now. If you take a conductor and connect a battery across this, like this, then this negative of the battery, the conductor contains plenty of free electrons in themselves, and they are not the electrons which have come out of some bonds. In conductors or metals, there are plenty of free electrons, and those electrons are not the electrons which have come out of the bond. They are the electrons which are free by themselves itself. Okay? These electrons will move like this. Okay? They produce current. Now, what is the direction of current? It is always from positive of the battery to the negative of the battery. Like this. That is the direction of current. Current is always opposite to the flow of electrons. Now suppose this is a semiconductor. How do the holes move? holes move in this direction, right? Because they have been repelled by the positive, attracted by the negative. Because electrons, when they go and fill the holes, hole gets shifted in the opposite direction. So holes will produce a current like this, and that is the direction of current itself. So total current in a semiconductor is current due to electrons plus current due to holes. Total current. You can add them. Even though they are moving in opposite direction, they are of opposite charge. So if you take the direction of positive charge as the direction of current, so this one, and direction opposite to the flow of electrons as the direction of current, that gets added up. So total current in a semiconductor is the current produced by electrons plus current produced by the holes. Okay, right. So in a semiconductor, if there are nh number of holes and e number of electrons, then the total number of charge carriers, number of holes plus number of electrons. That's how you count. Both will be responsible. Now, oh, I shouldn't have rubbed this one. Okay, I will try it again. In a semiconductor, if you observe, sir, then how many electrons and holes will be present? Definitely equal number. This is what I discussed above 0 Kelvin. Because at 0 Kelvin, number of electrons and holes are 0, right? At 0 Kelvin, number of electrons is equal to number of holes is equal to 0. Because no electron will leave the valence band. All the electrons will be in the valence band. They don't leave it. They don't go to the conduction band. So no holes are produced. No bond is broken. Atoms don't vibrate. All the bonds are intact. 4 valence electrons form 4 bonds with the 4 neighboring atoms. So no problem. Suppose you have 4 neighbors and there are 4 members in your house, and all the 4 neighbors celebrate some function at a time, but you don't want to disappoint them. So what you can do? You can send 4 people to 4 houses at a time and satisfy all the people. Similarly, 4 valence electrons in silicon, 4 neighbors, so take it, 4, right? So form the bond. So we have 2 hands with us. Our friend is also having 2 hands. We hold it and celebrate when we meet after certain time. Same way, right? Now, at 0 Kelvin, no bond is broken. Electrons are intact. No holes, no free electrons. Now, at room temperature, electrons can absorb energy, go to the conduction band. When one electron moves to the conduction band, form the valence band, and if that energy is enough to lift it, that more than energy gap. If the electron absorbs an energy which is sufficient to go to the conduction band, it moves. So an electron becomes free and a hole is created here. So how many electrons and how many holes? Equal number. 10 electrons go to the conduction band. 10 holes are created in the valence band. 10 bonds are broken. 10 free electrons. 10 holes. And those holes may be filled with some other bound electrons. And the holes may replace somewhere else, right? So 10 holes will move, 10 electrons will move. So if that semiconductor contains number of holes and number of electrons equal, then it is called intrinsic semiconductor. What do you mean by intrinsic semiconductor? Intrinsic semiconductor is a type of semiconductor where number of electrons and holes are equal. Why they are equal? Because the extra heat energy supply will create some free electrons, but when electrons go out of the bond, they create same number of holes. So that is intrinsic. And remember, this is a pure semiconductor. What are intrinsic semiconductors, if it is asked? Intrinsic semiconductors are pure semiconductors, naturally available, where number of electrons and holes are equal. And there are no impurities. There are nothing added from outside. External foreign impurities are not at all added to that. It is a pure semiconductor where number of electrons and holes are equal. But remember, this is only above 0 Kelvin. At 0 Kelvin, there are no electrons and holes, already have written. Now, actual characteristic of semiconductor starts from here. You can't use a semiconductor in the intrinsic form in technological field. You have to change it. Sir, can a semiconductor be turned into a very, very good conductor? Yes. How? By adding impurities into that. By creating more number of electrons and holes. Sir, how do you create electrons and holes? Do you supply heat energy and lift all the electrons to the conduction band? Such a process is very difficult to produce more free electrons and holes. We go for another process called doping. Doping means adding external impurity to the semiconductor. Once you add external impurity to a semiconductor, then it is called extrinsic semiconductor. So what is an extrinsic semiconductor? Extrinsic semiconductor is a semiconductor where number of holes and number of electrons are not equal, and into which it is not pure semiconductor, it is not naturally available. Some other impurities have been added to it. Now what do you mean by doping? The process of adding impurities to a semiconductor is called doping. Now how do you dope? Of course it is a very macroscopic level of work. It is done in laboratories, but how it is done? Theoretically we can see that. You know that every atom in a silicon or germanium, it is tetravalent. It contains 4 valence electrons. In addition to that, there are some electrons in the lower energy levels also. Don't be under the impression that there are only 4 electrons in silicon. There are electrons, but we are interested with the outermost electrons where the actions are taking place, forming the bond, neighboring atoms and all. So now take a silicon material and dope it with some other elements or atoms which are pentavalent, say. What is a pentavalent? For example, phosphorus, antimony, bismuth. They are all pentavalent atoms. They have 5 valence electrons and there are 5 neighbors. They share these 5 valence electrons with the 5 neighbors. Now if you replace one silicon with one phosphorus atom, what will happen? Suppose there is a silicon and a silicon here. I will restrict it to some silicon. Silicon is tetravalent. There are 4 atoms and 4 valence electrons, 4 neighboring atoms. So this is the bond. Okay. Right. S. Yeah. Now we will concentrate on this. There are plenty of silicon atoms. This silicon atom donates 4 valence electrons to its 4 neighbors. Of course, 4 neighbors will also donate valence electrons to this silicon. Okay. Now, suppose this silicon atom is replaced by one phosphorus. Of course, we don't add only one, we add it in crores. One phosphorus atom. Phosphorus is pentavalent. Pentavalent. What do you mean by pentavalent? Containing 5 valence electrons. Pentavalent. Now when phosphorus is replaced, of course this has to be done in laboratory, and silicon has to be replaced with phosphorus atom. When the silicon is replaced with the phosphorus atom, phosphorus, why do we choose only certain atoms like phosphorus, bismuth, antimony and all? Why can't you add a higher valence atom? There are some difficulties. We will see what are the conditions required for the doping atom. This is called dopant. The atom which is added to the pure semiconductor is called dopant. The process of adding impurity, that a pentavalent or trivalent atom to a semiconductor, is called doping. Now when phosphorus is added, phosphorus is pentavalent. When phosphorus goes and fits to that silicon atom and replaces the silicon atom, phosphorus looks into the surroundings. It looks and it sees only 4 neighbors, 4 silicon atoms. These silicon atoms, say, last time there was another silicon atom there and we were having a good bond between that atom. Now phosphorus, you came here and we want to form the bond, continue the bond. Phosphorus says, I have 5 valence electrons, no problem at all. I can give you 4 electrons for forming the bond. But what about the fifth one? Fifth one is free because it had 5 valence electrons. Remember, that is not an extra electron, because when silicon is removed, the whole silicon atom is removed. Its 4 valence electrons, the electrons in the innermost atom, innermost energy levels, everything is removed. It is replaced by the whole phosphorus atom. When the whole phosphorus atom is replaced here, it is a neutral atom. It contained 5 valence electrons, some electrons in the innermost energy levels, and equal amount of protons inside the nucleus. It is as a whole neutral. Only the difference between phosphorus and silicon is silicon was having 4 electrons in the outermost energy level and phosphorus is having 5 electrons in the outermost energy level. That is the valence energy level. So phosphorus is ready to make friendship with 5 neighbors. Silicon is ready to make friendship with only 4 neighbors because it has got 4 electrons in the outermost energy level. That means 1 electron is left free without any bond or without any bond between the neighboring atoms. This becomes the free electrons. And if you do like this with crores and crores of phosphorus atoms, then many free electrons are created. That is why we get an extrinsic semiconductor. This is not a pure semiconductor. Now suppose in this silicon material, I have simply for your convenience, I say in this silicon I have added 100 phosphorus atoms. Let us see like that. If there are 100 phosphorus atoms, okay, 100 phosphorus atoms added, then 100 free electrons will be created. Am I right? 100 free electrons. Sir, whether some holes are created? No, not at all, because 100 phosphorus atoms will replace 100 silicon atoms here and there, and all those 100 phosphorus atoms will be expecting 5 silicon atoms from surroundings, but there are only 4 silicon atoms in the surroundings. So each phosphorus atom will be ready to, or it will get a chance of engaging 4 valence electrons. 1 valence electron is left free. So each phosphorus atom retains 1 free electron as a free electron. It can't have any bond because it has 5 valence electrons where needed is only 4. So 100 free electrons are created because of 100 phosphorus atoms. 1 electron is left vacant free in each atom. Now no hole is created because that is not an electron which has come out of the bond, right? The 5th electron in the phosphorus atom, it is not an electron which has come out of the bond. So no hole is created, 100 free electrons. Now when this is done, this material may be at room temperature. Now because of heat energy absorption, some bonds might have been broken already between silicon atoms. Say 10 bonds are broken. When 10 bonds are broken somewhere else, 10 electrons might have been created free because that bond is broken. At the same time, 10 holes have been created because that bond is broken. Some electrons are needed to fill that vacancy. So there may be, because of heat energy, because of temperature, so because of thermal energy, there may be 10 electrons and 10 holes created. Say 10 bonds are broken. So what is the total number? Total number is 100 free electrons because of doping and 10 electrons because of thermal energy. 110 free electrons. We will add these electrons with this. Nothing will happen because they are free electrons, however, and there will be only 10 holes. So whose number is more? Definitely free electrons. So we call this, since negative charge carriers are more because of phosphorus doping, this type of semiconductor obtained by adding pentavalent impurity is called N-type semiconductor. And this is extrinsic. You know what is extrinsic? Extrinsic semiconductor is a type of semiconductor where number of holes and electrons are not equal. You see, number of holes is less than number of electrons. So extrinsic N-type semiconductor where number of electrons is more than number of holes. I can write it like this way also. Number of electrons is more than number of holes, and electrons, now free electrons are called majority carriers. They are majority carriers, and free holes are called minority carriers. Of course, they are also responsible for the flow of current. The main current is contributed by the electrons, not by the holes. So that is why free electrons are called majority carriers and holes are called minority carriers, which are lesser in number. Remember, these holes are not created by this pentavalent impurity. They are created by thermal excitation. Electrons absorb, some electrons may absorb the energy and break the bond, or they go to the conduction band, leaving some holes, leaving some bonds not completed, and that is a hole. So if you want many free electrons, you can add more phosphorus atom. But that dopant atom, that is dopant, phosphorus, is selected in such a way that it should exactly fit into this silicon place. The atom size should be comparable, one thing. Secondly, its crystal lattice shouldn't be disturbed. So when you replace many silicon atoms by phosphorus atoms, the strength of the material shouldn't be lost. Of course, the number of silicon atoms replaced by phosphorus atoms is very less compared to the total number of silicon atoms. But even then, the energy of the silicon atom, when it is replaced by a phosphorus atom, energy should be comparable, and the size of the atom should be comparable, the crystal lattice shouldn't be disturbed, and all those conditions should be satisfied. Then only this is possible. Otherwise, this phosphorus cannot continue the same work as silicon. So it should satisfy some condition if that dopant has to be replaced here. So selection of dopant atom should be very careful, and that can be done with the only certain atoms. Now this dopant is called donor impurity. Phosphorus is called donor impurity. See how many definitions have come. What is donor impurity? Since addition of phosphorus, which is pentavalent, has created one free electron extra. Since it has got 5, only 4 is enough for forming bond, 1 is remaining. Since addition of phosphorus created extra 1 free electron, the number of free electrons go on increasing as we add more and more phosphorus atoms. That is why phosphorus is called donor impurity. It donates 1 free electron, but it is not having an extra electron. Remember, the number of electrons, total electrons in phosphorus, and number of positive charges inside the nucleus are same. It is not an extra electron. So it donates 1 free electron. That is why it is called donor impurity. So you have plenty of conclusions to make here. Addition of phosphorus atoms, pentavalent atoms, creates 1 free electron. Such a type of extrinsic semiconductor is called N-type semiconductor, negative type, because negative charge carriers are more. Electrons are called majority carriers. Holes are called minority carriers. And what else? The type of semiconductor after once it is doped is called extrinsic semiconductor. And in a pure semiconductor like intrinsic semiconductor, which is not doped, number of holes and electrons are equal. Whereas in extrinsic semiconductor, they are not equal. In N-type semiconductor, number of electrons is more, number of holes is less, right? And holes are majority carriers, electrons are minority carriers. Of course, these things become very clear to you when I deal with the p-type again. Same type of story. When you don't dope this, when you replace silicon with the atom like boron, which contains only 3, it is trivalent, 3 valence electrons. So one bond is vacant, one bond cannot be completed. So such a type, it creates holes. So that continues. We will discuss it again in the next class. And I want to pose a question here. Think of and answer me. Answer me in the WhatsApp. I pose a question like this. I have a pure semiconductor which contains all silicon atoms. Everywhere the silicon house. 4 valence electrons, 4 bonds. Beautiful apartment. Now replace 1 silicon atom by a phosphorus. You have an 1 extra electron which is not having any job because only 4 valence electrons are enough. We get N-type semiconductor. My question is, After doping a pure semiconductor with a pentavalent impurity, the resulting semiconductor is called N-type semiconductor. Now N-type semiconductor is 1. Negatively charged, 2. Positively charged, 3. Neutral, 4. I don't know, right? The fourth option is very beautiful, I don't know. So what is the option, right? N-type semiconductor, that is a pure type of semiconductor. Once it is doped with the pentavalent impurity, it is a N-type semiconductor. It is negatively charged, positively charged, neutral, and I don't know. Answer me. Thank you for listening to my class. It is a very beautiful chapter. We will study it properly so that it is a very scoring chapter, as well as entrance for entrance exam. You can study it and remember it for a long time. So don't waste time. Hope you are doing enough amount of work, academic work, right? So thanks for watching my class. We will meet in the next class. Thank you.